Okay, here's lemma 2. So just to review, right, as of the last clip, we've started with a Markov chain X, which has one-step transition probabilities pxy's, right? I put one step in parentheses so I don't have to write them every time, because we also saw that there is a second chain that, all of a sudden is there that we were not aware of, perhaps. But that chain X prime has transition probabilities P prime XY, right? And if you kind of don't remember, right, this was the definition that we gave to the P primes. Again, every pi x is greater than 0, so these are well defined, right? So we have these two chains. We knew about the first one. We knew about X. We had no idea that there was going to be this X prime chain. And here's the lemma, right? So all of a sudden, right, we're kind of now asking, well, what are some of the properties of this chain X prime? And lemma 2 gives us a little bit of an answer to it. It's saying that X prime has stationary distribution pi. So we have two chains, not necessarily the same, right? There's no convincing reason as to why this has to equal pxy, right? So we have two totally different chains. Well, maybe not totally different, but clearly different. They're both on the same state space. We agreed that X was going to have a stationary distribution pi, and lemma 2 is saying, well, look, if that's true, then X prime, this chain that we didn't know was even there, also has stationary distribution pi. In other words, this pi is the exact same one as this pi, right? They share the same stationary distribution. So meaning that if you let time run for long enough, and both of these chains are kind of crawling on, right, the state space S, X is doing its own thing, X prime is doing some other thing, after a while their behavior looks essentially the same, remarkably the same, right? They're both gonna just appear to follow the distribution pi, right? So let time run long enough, they're both gonna be behaving in the exact same way, even though clearly the behavior, sort of when looking at sort of how they move from one state to another, does not have to be the same at all, right? So that's definitely something to digest, and we'll talk a little bit more about this, but for now, hopefully you're kind of coming to grips with what's happening, right? We have two chains, and they seem to be sharing the same stationary distribution, yet the two chains are also, we're also going to agree that they're different in some very clear way, namely their one-step transition probabilities are different. So, before we kind of get further into what this means, let's make sure that lemma 2 is true. This is going to be an even simpler proof. So how do we show that X prime has a stationary distribution pi? Well, you can try to check the global equations, the global balance equations, with respect to the P primes. So when verifying the global balance condition, right, we've already seen this before, don't start from the left-hand side and read from left to right. Let's try to read from right to left. And so if we were to start with this, which is 1/2 of the global balance relation, if we kind of go through a bunch of steps and get to this part, pi y, right? If we get here, then the proof is concluded, right? We know that pi is already a distribution, right? We don't even have to check this part, right? We know that pi is a distribution, that's even strictly positive on every single state. The only thing that you need to check now is global balance or local balance, but here we're going to go with global balance, right? We're going to check this global balance condition, right? So pi is now being verified to be a stationary distribution with respect to the P primes. We know that if I erase the P here, right, if I erase that prime there, this equality is immediately true. Why is that? by the fact that we're given that x has stationary distribution pi. Right. This is a more nuanced question. Right. It's not clear why that should be true. So let's plug things in. So I'm just going to write the same sum. Right. Pi x. So all I'm doing is plugging in the definition for p prime. Hopefully I've done this correctly. Give myself a little bit of breathing room, right? So all I've done was plug this into here, and you immediately see that these two cancel. And then what happens? I'm summing up over x something that doesn't depend on x. So this comes out of the sum. And then I'm summing over the second coordinate, right? I'm using the transition property of the pxy's here, right? These are transition probabilities, therefore from state y you have to get the sum x, and we're summing up over all x, and so you get pi y times the sum of x p y x, and this thing, right, is always equal to 1 no matter what, right, by definition of the fact that they're transition probabilities, right? And so this thing is equal to 1, and so you get that what we claimed is in fact true. And so x prime has the same stationary distribution as x, right? So things are getting kind of a little bit more mysterious. So now let's see what the third lemma has to say about all this.